Hello. Okay. So it's time to start. I'd like to welcome Professor Michael Mitzenmacher from Harvard University. Mike and I have known each other. I don't want to take too long. We've known each other for something like 2/3 of our lives, which is a little scary. He was heckling me before the talk, so I'm going to introduce him by pointing out that he's well known for his power of two choice work, as well as what he'll talk about today. But so when I wanted to invite someone, I thought, well, let me randomly pick two people that sound interesting. Unfortunately, Mike was the more interesting of those two people, so here he is. He's an ACM fellow. He's the Thomas J. Watson Senior Professor of Computer Science at Harvard. And with that, let me hand off.
All right, thank you. So part of this talk may be review for some people or a lot of people, and so one of the first things I like to do is just figure out how quickly I can run through the first slide. So let me ask as a little test, how many people here feel they're very familiar with Bloom filters? Like no one loves Bloom filters? Yeah, Steve was right, less than half. Okay, so I'm sorry for you people. You're gonna have a bit of a review. Hopefully there'll be something new in there. But we're gonna start by talking about Bloom filters, one of my favorite data structures. This is the world's best data structure that for some reason isn't in CLRS, the big white book, algorithms book, but everyone should know it, okay? So a Bloom filter, the job of a Bloom filter is to represent a set. So we have some set of keys or elements from some universe, and I'm going to want to answer queries of the form is, this query element y an element of the set, okay? Now, this is not generally a hard question, right? If you put things into numbers, you could imagine just keeping a sorted list and doing a binary search. There's all sorts of ways you could imagine doing this for different types of data. What the Bloom filter gives you is a very small way of representing the set, right? So what the Bloom filter provides is an answer in essentially constant time, the time it takes to hash a key, small amount of space, and the trade-off is that we're going to shrink down the space that's required by introducing some probability of giving the wrong answer in some systematic way. So let me, again, sort of formalize that a bit more. So we're going to have a data structure that's fast and small, but in terms of the probability of error, we might have some false positives. So it might be that something's not in the set, but we're going to actually end up saying that it is in the set with some, hopefully, small probability. Okay. There's also a potential if you were looking for types of errors that you'd have false negatives. You'd say something that was in the set but was not. A Bloom filter is going to only have false positives. It will not have false negatives. Okay. All right. So we'll get to some applications for why you might care about that in just a slide or two. But before that, here's just the one slide, like this is why this is such a great data structure. In one slide, I can present what a Bloom filter is. Okay? So a Bloom filter, we're going to start with a bit array filled with bits all set to 0 initially. Okay? We have a bunch of keys. What are we going to do with those keys? For each of those keys, we're going to hash each key k times. Where think of k as a small constant, if you like, right now. Okay? And our hash is going to give us an index into the array. Okay? So if the hash is, I guess, 2 here, the second bit will be set to 1, and so on. We're using one index arrays. Okay? So each item is going to be hashed, and if we get that bit location, we'll set that bit to be a 1. Something might get set to 1 multiple times. That's fine. That we don't add things up or anything. We just set it to 1. All right, so what do we do to check if something is in the set? Well, we're going to hash it k times and look at those k locations. And if we ever see a 0, right, then we know that this was not an element in the set. Because if this was an element of the set, that means that when we put it into the Bloom filter, we would have marked those locations as being 1s, but we've seen a 0. If we see all 1s, then we think it is in the set, or we report that it is in the set. And certainly if it was in the set, we will see all 1s and produce the correct answer, but we might potentially have a false positive. Right? It might be that it's not in the set, but we somehow unluckily saw all 1s when we looked at those hash locations. Any questions? Yes. Yeah. So I'm going to hash it k times. There are k different hash functions. So each time I hash it, I'll get a location, right? And I'll just look at those k locations. Okay. All right, so the important thing is, well, what is that false positive probability, right? If I'm getting lots and lots of false positives, then this isn't necessarily a particularly useful data structure. Okay? So let's first figure out what's the probability that a specific bit of the filter stays as 0. Okay? For it to stay as 0, I have to miss that bit. That happens with probability 1 minus 1 over m. I have to miss that bit kn times. I'm hashing n elements. Each is being hashed k times. So there's kn total possibilities or times that I might possibly change that bit from a 0 to a 1. So the probability a specific bit of the filter is 0 is that expression up at the top, which is about e to the minus kn over m. Okay. Now, if rho is the fraction of 0 bits at the end of the day, then the probability I get a false positive on some new element is the probability that I see 1 bits, which happens with probability 1 minus rho, all k times. Okay. Now, what is rho? Rho is the fraction of 0 bits in the filter. That's going to be very closely concentrated around its expectation, which is p prime. Okay. Now, p prime is approximately the same as that p-value, e to the minus kn over m, for largish of values of n and m. Just an asymptotic approximation, makes things easier to write. Okay. And c there is the ratio of m over n, the number of bits per item. And so I get the final expression for the false positive probability right over there. And given that, I can do things like ask, well, how many hash functions should I use? You can just take the derivative. A little calculus tells you that k equals log 2 m over n. Remember, m over n is the number of bits per item, gives you the optimal. And then you can plug that in to find the false positive probability falls exponentially with the number of bits per item. It falls at about a rate of 0.6185 to the number of bits per item. Okay. If that math bothers you, here's like a nice example, just as a graph. Okay, so here, m over n is 8, so I'm using like 1 byte essentially per item in terms of the array. And I can ask what the right number of hash functions is. I can think of it as a continuous function, draw the function, and I find the right number of hash functions is roughly either 5 or 6. And at 5 or 6 hash functions, I get a false positive rate at about 2%, just over 2%. And if you wanted it down below 1%, you could just throw 2 more bits per item at it, because it's falling exponentially. So one thing that's interesting about this behavior, right, is that you can see that the probability is depends on how it depends on the number of hash functions. It falls and then it starts to go up again, right? Like one way of thinking about this idea of how many hash functions should we use, right, is that there's sort of 2 effects, right? So let me throw it out to the audience again as a quiz. Can someone give me a reason why should I use more hash functions? Right? Why would your intuition be I should be using more hash functions in my Bloom filter? Yeah. Right, you have more chance, exactly, thank you. You have more chances of finding a 0 when you look at the array. Okay? Now can someone give me some intuition, why should I be using fewer hash functions in my Bloom filter? Yeah. Right, the more hash functions, the more ones I'm filling it up with to begin with, right? And the more ones I'm filling it up to begin with, the more chance of a false positive. So of course, these 2 things trade off against each other, and you can sort of see that in the equation, right, by the fact that there's a k in 2 places here, right? One inside that, 1 minus e expression, one outside. One's helping you, one's hurting you, and calculus tells you where the right trade-off point is, and that's why you get a curve that looks like this. All right, just some additional notes, like often it makes sense to split up the Bloom filter, so you take your m bits and split it up into smaller subtables the size m over k, and hash to 1 location in each subarray, right? So you still have m bits, but you're just picking one from each subpart, that really has essentially the same performance. There's a small gap that disappears asymptotically. It can be easier to parallelize, for instance, in systems where you want to send off those hashes in parallel. All right. Now let me suggest that Bloom filters are great, but they're not necessarily the optimal way to solve this problem, depending on your setting. Like, what's another way that you could solve this problem? Another way you could solve this problem is to use a perfect hash function, right? So for a perfect hash function, you're given a set, and you find some hash function that puts each element in its own place. Okay? So here I'm thinking of a 5-element set. I can find some hash function that maps each element to its own location. And then what I could do is store a fingerprint, which I would obtain from another hash function, of each item in the cell. Okay? So now, in order to do a Bloom filter type lookup, is it in the set or not in the set? You give me an element. I hash to figure out what bucket it should be in this perfect hash table. I then check the fingerprint. If the fingerprint matches, I say it's good. Otherwise, I say it's not. Right? And there, the false positive probability falls a little quicker. It falls like 2 to the number of bits used for each of the fingerprints. Right? Right, so the false positive probability there falls like 0.5 over m over n instead of the 0.6185. Right, so it's a little better, uses less space, about 40%. Okay? A downside is that, first of all, I'm not counting the cost of storing whatever that perfect hash function is, right? And those exist, but they can be a bit expensive. And the other thing is that it's less flexible. Like with a Bloom filter, I could always add a new item if I wanted to. I could just hash the new item, put ones in the right places if I wanted to add an item into the Bloom filter. For this solution, I couldn't quite do that because I'd have to, if I wanted to add a new element, I'd have to come up with a whole new, brand new perfect hash function for the bigger set. But this alternative construction will come back later on in the talk, or the idea behind it will come on later in the talk. So that's why we're sort of looking at it now. Okay. All right, so we've already said Bloom filters are, are not optimal, so why use them? So I always like presenting Bloom filters, even my undergraduate algorithms class, because there's a really nice trade-off thing here. Like, students are used to considering trade-offs between time and space, but it's fun in the introductory algorithms class to introduce them to the idea that correctness is just another trade-off parameter, right? That I might want to trade off the probability of error against time and space as well. It's sort of a concept that, like, I think for undergrads kind of blows their mind, right? That correctness is something that you can trade off as well. And this is like just a very simple fundamental example of that. And the other thing is that, in this 4-dimensional trade-off space world, there's another trade-off factor that you'll never see in any theory class, which is the time it takes to implement. And Bloom filters are just dead simple, and people understand them. So people who actually write code tend to like Bloom filters just because it's like they're easy to whip up and code the way you want them to, and they understand how they will work. So like one of the early uses of Bloom filters had to do with spell checking, which seems like a silly example today when we have memory everywhere, but long, long ago, memory was like a scarce resource. So if you put yourself into a scarce resource world, you might say, well, I don't want to keep a whole dictionary around in memory, but I might be able to keep a Bloom filter of a dictionary in memory. And now the question is, well, what happens when I get a false positive, right? That means that a misspelled word will be accepted. So if you can get, your false positive rate low enough, maybe that's okay. Maybe not. You have to decide if you're willing to deal with the issues of false positives. And there have been similar places where Bloom filters have been used to deal with things like lists of words, like lists of good security words, keyword-driven ads, and so on. Bloom filters are used in databases to do what's called a Bloom join. So the idea is that instead of sending a list of all the records that you want from another side, like please give me everything that matches A, B, C, D, E, F, and G, you send them a Bloom filter of that list of things you'd like matched. They use that to determine possible matches and send them back to you in this distributed database world. So you might get some extra items because of false positives, but you end up sending less information total because you're sending the Bloom filter of the list of things you want instead of the full list. More recent place where Bloom filters have been used is for signature detection. So this is like a security type setting. You're looking for, bad substrings associated with worms or viruses and so on within a packet. And you want this to be fast and so run easily on hardware. So you separate the bad signatures that you have to check for by length, build a Bloom filter for each length, and then essentially as each character comes in, you can pipeline through and in parallel check all the strings of the last however many characters for each appropriate length. And if you ever see one of those bad signatures, then you say, well, I have to send things off for further examination to determine if this was real or a false positive or what I should do for this situation. All right, and if you haven't seen Bloom filters, these are now used all over the place, particularly in networking and in security. I have some surveys on their uses, but there's more and more of these things popping up everywhere every day. All right, good time for a quick pause and any questions before I go on to the next sort of semi-review item. All right. All right, so the main takeaway from this first part for those who have to leave or want to go to sleep now, the main point is that whenever you have a set or a list of items and space is some sort of concern that you have to deal with, a Bloom filter may be the right useful alternative. You just have to make sure that you consider or figure out what are the effects of the false positives, what are they going to do to your system. There are some settings where false positives are okay, you can handle them in a sort of off path, and there are other cases where false positives might be just terrible. So you really have to think in terms of what it will do with your application. Bloom filters, just to point out, again, this will come up later, there's no natural way to delete things from a Bloom filter, right, once you've created the Bloom filter, because if I have two items, xi and xj, that I've put in the Bloom filter, and they share a location, and you think, oh, I'll take something out of the Bloom filter by changing those ones back to zeros, now you might be introducing false negatives. You might have some item that you've accidentally taken out of the set by setting the 1 back to a 0. One way that this can be fixed in practice is to use what's called a counting Bloom filter. So now instead of just your Bloom filter being an array of bits, it's an array of counters. You keep a count of how many items have hashed there. Okay? And to delete an item, you just undo or decrement the counter, and there's an associated Bloom filter that you can get by reducing non-zeros to 1. And typically in this sort of setting, you might be doing insertions and deletions a lot less frequently than lookups. So you might keep the larger counting Bloom filter in slower memory and only update it when you're doing those slower insertion and deletion operations, and keep the fast, smaller Bloom filter in memory for lookups. And if you're doing that, and I'll just skip through this quickly, but you should worry a bit about, well, if I'm keeping a counter, what if that counter ever overflows? That would be bad. But you can show that with the math that the probability you ever have to worry about overflow, if you're setting parameters right and using even just 4 bits per counter, is small enough that you really shouldn't be worrying about it. Right, this is just what I was saying before about keeping a CBF in off-chip memory as opposed to on-chip memory. Okay. All right, so the next topic, which I'm going to bring back later and have it relate to Bloom filters, is Cuckoo hashing. Okay. So Cuckoo hashing is a way of developing a nice, friendly type of hash table. And the basic scheme looks like this. So normally in hashing, we hash an object, we find a location for it, and then we think of that as a bucket. And if we have lots of things in the bucket, then we have to do some sort of chaining or something to keep track of the multiple things within a bucket. Okay. So in Cuckoo hashing, we're not going to have chaining. right? We'll just say there's going to be just one element per bucket. That's going to be it. So how are we going to deal with collisions when we have our hash table? Well, each element is going to have not one possible location, but two possible locations. So we use two different hash functions. So to insert an object, we check if either location is empty. If it is, all well and good. If they're both full, then what that element will do is kick one element out, say at random, and tell it to move somewhere else. And that element has somewhere else to move because it had two choices. So it will go to its other choice, and it may have to kick something out, and so on, until everything hopefully comes to rest. Okay. So what does this look like? So here in this picture, I'm using like a split version of the Cuckoo hash table, so you get one choice from each subtable, and the arrow is telling you where your other choice is. Okay, so a new item, F, comes in. Both places are empty. It could go in either one. An element G comes in. Both the items are full. Let's say it goes to where the A is. So it's going to knock out the A, which will knock out the E, and so on. So the E gets placed and everything, gets placed happily. All right. Can someone tell me what happens in this setting when I try to put in the element G? What? Yeah, there's no place to put it. It will end up looping infinitely if I try and keep kicking things out, right? So one easy way to see this is like you can see that there are 7 things that I'm trying to put into a total of 6 buckets, right? So mathematicians will tell you you can't put 7 things into 6 buckets. They call that the pigeonhole principle. Everyone else calls it common sense. And right, so that's a bad case for cuckoo hashing, right? But all right, so the idea is that should be a rare occurrence, or we don't want that to happen too often. All right, so one of the good properties of cuckoo hashing is as a worst case constant lookup time. When I'm looking something up, I have 2 places to look. I just look at those 2 places. Okay. You can get high memory utilizations, as I'll describe. Again, it's simple to build and design. The thing you have to worry about are failures. In particular, you could run into a cycle, or maybe you want to have your insertions complete in a reasonable time, and there's some long path you have to take to figure out how to insert a new item. So the point is that we can show probabilistically that bad cases occur with very low probability. Okay? And when a bad case occurs, at least in theory, we could possibly rehash everything. Say, OK, I'll pick new hash functions and try again. Okay? In theory, that solution's OK. In practice, maybe you don't really want to rehash everything, so we really want to try and keep that rehash probability low. Okay? So the basic theoretical results are that if you have 2 choices and your load is less than 50%, that is, I have like 100,000 cells and I'm only trying to place fewer than 50,000 things, then the failure rate falls like 1/n, and the insert time will be logarithmic. And you can just think of this in terms of a random graph representation, where each element is an edge and the buckets are the vertices. And then you can say that what a cuckoo hashing table gives you is a random graph. And then you can use well-known facts about random graphs, that if the load is small enough, that if the load is less than 1/2, then your random graph will have only small, that is like order log n size, acyclic or unicyclic components. And so the result just sort of falls out of random graph theory. There are all sorts of natural extensions to this. You might say, well, if 2 choices is good, maybe 3 choices is better. Okay. So you might say more choices per element. Or you might say maybe you can put more than 1 element in per bucket, or some combination of these things. And in fact, both of them really improve the load that you can achieve. So for bucket size 1, I keep forgetting to change this slide. That should start at choices 2, then 3, then 4, right? Or you can think of that as additional choices, I guess. But yeah, so 2 choices, the threshold is 0.5, like I said. But at 3 choices, it jumps up to 91.8. And by the time you're at 4 choices, it's 97.6. So those are asymptotic theoretical. In practice, you get slightly lower than that. But you can achieve well over 90% utilization, even with 3 choices, and even more than that with 4 choices. Similarly, if you have 2 choices but increase the bucket load, like you have up to 4 items in the bucket, you can get up to like 98%. So one thing we might want to figure to do, like I said, is how can we keep this failure probability low? Okay. Well, these failures are these sort of rare situations where some sort of cycle happens in the 2 choices, or some part of the table, some local small component gets overloaded. So typically, when you get a failure, it will be like this one bad item that's hurting you rarely. So what if we could just say, well, sure, if you have one item that fails, let's hold it off to the side. Stop trying to put it in the table if it won't go into the table. Let's have a small stash of unplaced items. And we can always, if the stash is non-empty, we can always go look at the stash whenever we do a lookup. As long as it's small, it won't be a big deal. And we have results that show that the probability of failure, right, falls like 1 over n to the size of the stash, right? So, or I guess size of the stash plus 1, right? So when there was no stash, it was 1 over n. The stash of size 1 will make it fall like 1 over n squared, and so on. So as an example, in an experiment using 10,000 elements in a table size 24,000, doing lots of trials, 99.9% of the time we never needed a stash. But even when we needed a stash, it was almost always stash of size 1, and we never actually even needed a stash of size 4, right? So a stash of size 4 gives you lots of protection against additional failures. Okay. All right, so that's it about Cuckoo hashing. And now let me start to bring some of these topics together. So how we get better Bloom filters by using hash tables. Okay, so remember I talked about using perfect hashing to develop a Bloom filter, right, by just keeping a fingerprint of each item in a big hash table, a big perfect hash table. So perfect hash tables are hard to build, right? How do you build a hash function that nicely maps each element in a set to a proper location, right? And as we said, it's sort of brittle. It doesn't work very well if I'm trying to insert and delete things. So maybe instead of having a perfect hash table, what if I use some sort of near perfect hash table and try and build a Bloom filter that way? What could I possibly do in that setting? Okay. Right, so again, remember this was the perfect hashing approach. So the update to this idea is, well, what's a good possibility for a near perfect hash table that I might use? Well, a Cuckoo hash table seems to fit the bill, so we can talk about what we'll call a Cuckoo filter. Okay? So instead of having a perfect hash table, we'll have a Cuckoo hash table. We'll store a fingerprint of each item instead of the element itself. It turns out that this can also support insertion and deletion of keys, right? So insertion up to the load threshold, deletion just by removing the appropriate fingerprint. And while there's some, it's not a perfect hash table, so there's some additional overhead, it turns out to work very well. Okay? So the idea is I'm going to use some sort of Cuckoo hash table. Type of hash table I'll use typically might have 4 items in each cell. So to test if an item is in my set, like so here I'm thinking of big sets, millions or maybe even billions of items. To do a lookup, I hash to find the cells in the Cuckoo hash table. I look and see if the fingerprint is anywhere in those buckets. If it is, I say yes, that's an element of the set. If not, I say no. Now, an issue is that for the Cuckoo filter, so let's consider the case where I have 2 choices per key, 4 fingerprints in each bucket. And if I'm using a Cuckoo hash table and I'm inserting items into it, maybe at some point the buckets are full and I have to move things around. So how do I move things around? Well, if I'm keeping a copy of the items, then I can do it, certainly. But I might not want to be keeping a copy of all the items around, certainly not in memory, and I might not even want to be keeping them around at all. Okay? So if we have all the items, then I can certainly go back and figure out how to move things around. But otherwise, how do I know where to move it in the case where I don't keep the key anymore and I just have the fingerprint? All right, so here we're going to do something that's theoretically unsound, but engineering-wise seems to work out very well, which is that for my two hashes, I'm going to hash the element, but then for my second choice, I'll take that hash and I'll XOR it with a hash, not of the element itself, but with a hash of the fingerprint. So the plus of this is that whenever I have an element and I need to move it, I can figure out where to move it to. I just hash the fingerprint that I want to move and find its other location. Okay, so I can move things around. Okay. The downside is that now my two hash values are not completely random, right? Because the second hash is not fully random. It depends on the fingerprint. In particular, if the fingerprint is small enough, the second hash function won't be uniform over all possible choices. It will just be uniform over a small subset of the choices. Okay, so there's upside and the downside. Right? The downside being, as I said here, these two choices are now limited. They're not completely random. Will this still work? And so in practice, we find, yeah, it works really well. Like, at least up until the billions, we don't see a particular change in the load threshold based on using this idea. Right? Theory sort of tells you, well, this really shouldn't work. Yeah, you should have something that's more random, right? And to do that, you need to at least have logarithmic size fingerprints so you could be uniform over the total space of hashes. Okay. But it turns out that, like, if you look closely at the theory, what it tells you is, like, for buckets of size b, the total number of bits you need is something like log n divided by 2b. So if we're using 4 elements in a bucket, your fingerprint, the theory tells you, should be like log n over 8. Log n over 8 is a constant, right, for most real numbers, right? Or, yeah, you can get pretty big numbers and have log n over 8 be pretty small. And so the theory is sort of telling you, yeah, like asymptotically, you might need big fingerprints, but in practice, you actually will be okay. There's some recent work, if anyone's interested in this, by David Epstein that has some provable bounds on the performance of partial key cuckoo hashing that are worth looking at as well. Once you have your basic cuckoo filter, there are some tricks you can use. Since every bit counts for space purposes, if we have buckets of size 4, a little trick you can do is to sort the 4 fingerprints. And then, based on the fact that the fingerprints are sorted, you can take the 4 most significant bits of each of the 4 elements. Normally, that would be 16 bits. But because they're sorted, the number of possibilities is reduced. So you could store those 16 bits and 12 bits of information. So you can save a bit per item that way, if you're into bit tricks to save bits. And the sort of performance that you get is that, once you start getting, here's the false positive rate, starting very high and getting smaller, going this way. And what you see is that very quickly, the cuckoo filter, or the semi-sorted cuckoo filter, the one where we shave off that extra bit, very quickly, like once you're below false positives of about 3%, start to be formed better, and they seem to follow the slope more closely with the lower bound result. So you're getting pretty close to the lower bound when you're using the cuckoo filter. Okay. So some recent work we've done says, okay, now that you have the Cuckoo filter, or general for Bloom filter data structures, it would be nice if they were adaptive. Okay, and what do we mean by adaptive here? Okay. So when I've talked about the false positive probability, I was really thinking about that in terms of like a single item. Like you give me a query that's not in the set, what's the probability I give you a false positive? So often when you're actually using Bloom filters, you're using them in a setting where you're seeing a data stream, like a list of queries. And sometimes those queries can be repeated. So if we're looking at, for example, in network security, where you might use a Bloom filter as an initial stage for like a whitelist or a blacklist, you might see certain URLs or certain network addresses over and over and over again. So that means if you get a false positive on it once, right, you're going to keep getting false positives every time you see it. So the idea is that there's really two different quantities we're talking about here. There's the false positive probability, which we can think of as being for a single element that you're asking for, and a false positive rate, which is over a data stream, and which might depend on the content of the data stream and how often it's repeated. So to be adaptive, what we'd like to do is if you see a false positive, you'd like to try and make sure that you don't see the same false positive again. Or in particular, not again and again and again and again, if that query is asked multiple times. Okay, so you can modify the Cuckoo filter that we talked about to allow for adaptivity. So a big restriction is that here you really do need to keep the original items around. Okay, so we're going to have a mapping. We're going to keep like the Cuckoo filter in sort of the quick memory where we're doing all the queries, and then we'll have a backup table that maps to the Cuckoo filter where all the original items are held. And in some sense, like, of course you'd need to do that in these sorts of settings because whenever you get a positive, it might be a false positive, or you're going to have to do some sort of additional processing, right? So even just to check if you got a false positive, you'd have to have the original items around. So this will really only make sense in cases where we don't mind, even if it's in slower memory, keeping the original data so that we can check for false positives. Now, the way we're going to deal with the adaptivity, right, is that, remember, we're keeping fingerprints for each of the keys. Okay, so what we can do is if we see a false positive, right, we see a match that shouldn't have been a match because it matches one of the fingerprints, is we'll go ahead and change the fingerprint associated with our key, but in a systematic way. So in the case where we have buckets of size 1, one thing that we can do is just keep some number of extra bits per cell to keep track of which hash function we're using for the fingerprint. Right? So we could keep 2 bits in a cell, and that would tell us, hey, you're using hash function 0, 1, 2, or 3. And if we ever see a false positive match, we say, OK, let's go ahead and change the fingerprint for the key that's held here. Okay. So when we do a lookup, you'll check the element against the fingerprints. If you see a match, make sure it's a true positive. It's a false positive, you just increment the counter, which tells you which hash function you're using. That will change the hash function. You correspondingly change the fingerprint. Hopefully you removed this false positive, and hopefully you didn't end up creating new ones. I won't go over it because we're short on time anyway. But we do some theoretical analysis of this in a mathematically tractable setting where we assume that the set items are independently, or the non-set items, sorry, are independently and uniformly generated over an interval. And I'll show some experimental results which show in some sense that seems to be the worst case for us. If the results are skewed, we actually do better. And we can figure out the probability of a false positive by doing an analysis of the distribution of the number of elements that hash to that bucket. We use the fact that that's approximately Poisson, and then use that to figure out the false positive probability per bucket, and then overall the buckets. An alternative approach, if we were using 2 hash functions, 4 cells per bucket, is to just use a different fingerprint for each cell location, right? So we have 4 items within the bucket, right? Remember before when we were talking about the Cuckoo filter, we said, oh, well, we can shave a bit by ordering them in a nice way by sorting them. So here we're going to use the fact that we can reorder the elements in a different way. We're going to say, OK, we'll use a different hash function for each location. Okay? So if it turns out that I get a false positive, what I can do is say, oh, I'm going to put this in a different location within the bucket. I'll swap it with something else within the bucket. That will change their fingerprints, and hopefully that will get rid of the false positive. Again, we can analyze these sorts of things. We've done some large-scale simulations, some of it just with artificial data, some of it taken with data based on network traces, using the 5 tuples as keys, separating some of them out to be ones placed in the filter, others to be the queries that we'd ask. And this chart may be a little hard to make out, but roughly what we can see is that if you look at the blue stars versus the red, right? So here's sort of the random tests where elements are chosen uniformly at random, that we can get as long as we use the appropriate number of bits. So let's see. So this is using the ratio of the number of non-set elements to elements as queries, the ratio 10, 100, 1,000. The top chart is using just 8 bits per cell for the fingerprint. The bottom is using 16 bits per cell as the fingerprint. So at 8 bits per cell, the adaptive Bloom filters start to do better as long as there are enough queries per element. And when you actually get to using a more reasonable number like 16 bits per cell, we can get things that look like order of magnitude or more improvements on the original Cuckoo filter in terms of the number of false positives by making use of this adaptivity. So wait, those were for random tests 8 and 16. These are for the actual Kaida test for 8 and 16. And again, we tend to get like orders of magnitude improvement. The skew only helps us. You can sort of see this, that if I have something that's being asked for like 1,000 times and it happens to get flagged as a false positive, right, it's really important that it gets fixed. So not only does the fact that there's skew end up like lowering, gives us better performance, but in some cases you can see here at 16 bits per item, you can get very wild behavior from the Cuckoo filter depending on how lucky or unlucky it was in terms of how often the things that end up being false positives were repeated or not repeated, because those can vary by orders of magnitude or more on any given instance. Whereas once you start to be adaptive, you only see like a couple of 1 or 2 false positives for a given item before you correct it and it disappears. All right, so overall our adaptivity concerns, our theory turned out to be pretty accurate, even though I didn't go over it much here. We get even better performance on real-life skew data. We get that the 2 choices, 4 elements per cell, is a pretty good standard configuration, and it can reduce the false positives by an order of magnitude. All right. And in the last few minutes, I'm going to talk about something really quite new. So new that I've blogged about it in the last month. So I have a blog called My Biased Coin. If you find this at all interesting, I'm going to point you to there to look at it. But there's sort of a new idea that came out over Christmas about how to do Bloom filters involving machine learning. Okay, so this group from Google Brain put out a paper, and they'll be happy if I advertise this paper. So how many people have seen the case for learned indexed data structures paper from the Google Brain? Some number of people. Okay. So there's a bit of hype about this paper. And one of the things they said is we can use machine learning to try and do something better than a standard Bloom filter. Okay? In a way that's very data dependent, right? So I should give this caveat that their approach is data dependent, whereas a Bloom filter sort of works regardless of what the data is. So there are certainly differences, right? And the idea is that suppose we have a set that has some sort of structure to it. Okay? So we might not even know what that structure is, but we can always throw learning theory at it, and learning theory will, if it's a suitably structured set, will be able to give us some sort of oracle, some sort of function that it learns, which can, given an element, will output a number that corresponds to something like a probability that the element is in the set. So this you can think of as some sort of black box. Google Brain people think we're great at machine learning. If you give us a set that has some structure to it, URLs on the whitelist, say, that you might think, those, or a blacklist that have some sort of structure to it, we will try and learn it. And by learning it, we mean we'll develop some sort of function that tells you whether you should think this is an element of the set or not. Okay? So hopefully this should give few false positives. Okay? But you'd like to use this function to develop a Bloom filter structure that will hopefully give you few false positives overall and should never give you any false negatives. Just like a regular Bloom filter. Okay. All right, so how do they suggest doing this? Right? So when an input comes in, you send it to the learned oracle. Okay? And it will choose a threshold. Okay? So if the probability is above some threshold that you can choose, right? If it says, okay, I believe with probability 0.9, this is a member of the set, you say, okay, this is a positive. And that might introduce some false positives. Okay, but that's fine. Bloom filters have false positives. We're all okay with that. And everything else will be a negative. Now, the problem is that those negatives may contain some set elements. It may be that you set the threshold at 0.9, and 25% of the set elements actually come in at 0.85 or something. So they're just below the threshold. Okay. So then what you do is build a backup Bloom filter to catch the set elements that weren't correctly classified by the oracle. Okay. All right, so that will also introduce false positives, but then everything else will get sent off as negatives. And the idea here is that if you can catch most of the positives by the oracle so that there are few set negatives coming here to the backup filter, then this backup Bloom filter can be small, right? If it's only 25% of the elements from your set end up coming to here, you can have a Bloom filter that's about 25% as big. Now, you also need space for whatever your magic machine learning function was, but that can be small too. And so if the total size is smaller than your original Bloom filter, you've saved space and gotten the same sort of performance. All right, so you go to my last couple of posts on my blog or check the archive, there is some caveats here, like the sort of guarantees you're getting out of this learn Bloom filter are different than the guarantees you get from an actual Bloom filter that could be important, right? So it's worth making clear what the sort of statistical guarantees you get are. And then the other thing that I notice is that you can actually do better than this sort of structure by using what I call sandwiching. And what do I mean by sandwiching? Right. So it turns out that instead of spending so much space on this backup filter, it turns out that the right thing to do is sandwich your oracle between two Bloom filters. You have an initial Bloom filter that throws out a lot of negatives to begin with, and the only thing that will come through the original Bloom filter is your set plus some small percentage of false positives. Your oracle will now work the way that the learned Bloom filter did before. It will put out the positives, pass through the negatives. You'll still have to catch the negatives that are in the set. But it turns out that what the math sort of tells you is that you're better off using some of that space for the backup Bloom filter to actually throw things out at the top, not the bottom. Right? If you think about it, the Bloom filter at the top and the Bloom filter at the bottom have different purposes. The Bloom filter at the top is to try and throw out as much stuff as possible at the beginning so you don't have to deal with it. The Bloom filter at the bottom is just trying to catch the false negatives that somehow got through the oracle and make sure that they don't actually become false negatives. And so what you want to do, the right optimization, is divide up the bits between those two tasks properly to minimize the false positive probability. And again, that's described in my blog and on some short notes I put up on the archive. So for people who've seen that learned index paper and thought it was interesting, there's some more stuff on that coming out. All right, so happily, I'm done more or less on time with maybe even a minute or two for questions. Right, so the key takeaways, if you haven't seen Bloom filters and Cuckoo hashing before, they're nice things that everyone should know. In particular, if you're going to use a Bloom filter these days, I'd recommend that you use a Cuckoo filter, which improves on Bloom filter constructions. And if you look up Cuckoo filter, when we did the paper, the other authors did a nice job putting up some code out on GitHub that gives a pretty solid instantiation that you can just plug into whatever project you're using. So if you want to try using a Cuckoo filter in your project, the code's already right there for you to just use and plug in. The nice thing about these sorts of data structures, Cuckoo filters, adaptive Cuckoo filters, and so on, is that they do the job of keeping things simple while allowing for high load, which is what you really want in these sorts of systems. Things that are easy to understand and code up, but also that have good performance. For adaptivity, there's a downside that to be adaptive, you actually do have to store all the elements because you're going to have to be checking them for false positives. On the upside, you get a large reduction in the overall number of false positives in many practical situations. So in terms of like open problems or things I'm still thinking about, like are there other structures or places where this adaptivity can be useful and how can it be implemented? And how should we be thinking about these learned data structures, like where we're plugging in these machine learning oracles into our data structures? Where are other places where this idea might be useful? So I think I'll end there. Thanks. Okay. Does anyone have any questions? Yeah. So the question was, in real life, what sort of hash functions do you use? Typically, like standard hash functions end up working pretty well. So the murmur hash is a frequent one that's used in practice. If you want sort of theoretically sound results, you probably want to use something that like tabulation hashing or some k-wise independent hash function for a suitably large k. And there are some efficient implementations of those. in real life, people often do not use theoretically sound hash functions, but they often work just fine. So it depends. Yes, there are both ones that have some sort of seed that you'd put in, and others that just are hash functions that are actually deterministic, but look enough like hash functions. Yeah. Mhm. Right. So here at least, like eventually, if someone's being adversarial and probing in, right, you're either going to have to be sort of growing in space to cope with that, or eventually you'll have to like re-randomize things, right? So, this I think in the it's hard to come up with what a right notion of adversarial setting is, but right here in this case, if you get a false positive on an element, right, if someone pokes and sees there's a false positive, well, then you've changed it. So that's no longer a false positive. So now they have to find a new one, right? So, this should make things much harder for an adversary to try and thrash you in terms of trying to stack you up with false positives. I mean, that's almost like one of the points of it is that once there's a false positive, if the adversary notices it, they can keep sending the same key again and again. They can't do that quite as easily here. Although eventually, if they keep throwing enough stuff at you, because we're keeping the table size fixed, eventually that will happen, and you'll either have to re-randomize or make the table size bigger. There's some nice work by Michael Bender and others that is also looking at adaptive hash tables, and they do these things where they like grow things out, right? So they, instead of changing the hash function, they actually like keep adding bits. And that might be another approach, but again, it sort of runs into the same problem that if the adversary is going to find things and be able to keep using them, you have to change in response. You're either going to have to change the size or re-randomize.